This is the video walkthrough of the NXTP SDK. So the purpose of the SDK is it is a JavaScript package that is available on NPM. It works in both the browser and Node.js, so it can be run anywhere. And the purpose is to interact with the NXTP protocol. So overall, at a high level, the SDK will manage the process of taking user requests to do a cross-chain transfer, publishing messages for auctions, collecting responses for the auctions, and then preparing transactions on the sender side. Then once the transaction is prepared on the sender side, the SDK will wait and inform the user when the router prepares the transaction on the receiver side. Then the SDK will prompt the user for the signature and then either broadcast to a network of meta transaction relayers who can fulfill the transaction on the receiver side, or send the transaction themselves on the receiver side. Of course, it emits events for everything as well. So first of all, the main entry point for the SDK is the index. So the index doesn't do anything, it just exports from the SDK. The SDK.ts is the main file in the SDK. So this is the top level overall class that contains all the functionality and all the high level functionality and is the entry point to the subclasses. So at the start, we have some constants defined here, which are just some minimum like hard-coded expiries and expiry buffers that will be checked later. We declare a global Ethereum constant because we're using the window.ethereum. This, I'm realizing now that this might have to be changed for like Node.js context where we might not have this. This is probably fine for now because we're only using it in the browser, but eventually we need to deal with this. So then we define a schema here. So this is a like schema definition that can be checked to validate the structure of parameters that are passed in. Then we define events here. So we have certain events that we emit from the SDK. So token approval, token mined, transaction prepare submitted, which is what before the transaction actually gets mined, we give a notification saying that it got submitted. Then when the actual transaction is prepared, we get another notification. This means the transaction went on chain and we received the event from the contract. So these three events all come directly from the contract. Receiver prepare sign, that means the user actually signed. So we prompt the user to sign, which would pop up MetaMask, and then we get a receiver prepare signed event. Then the last three events, receiver transaction prepared, fulfilled, and canceled, these come directly from the contract itself. And we'll see how these work a little later. Then we define event payloads for what the various event responses are. And then we map the events to the event payloads. This gives us nice typed structure in the event handlers. So the event handlers can be called and attached, and you get like a typed data payload. And just some boilerplate for the AGV stuff. So create EVTs creates the container of event emitter EVTs, which contain the payloads as we referred to before. And because we do this mapping, we can actually use the event, this event like property to actually map to the proper payload. Then we define a specific error class for NXTP errors. So we have nice typed errors and various reasons and contexts that we can throw in there. So this is the main NXTP class. It has an EVTs as private member. It has a transaction manager, which is the wrapper around the transaction manager contract. We'll show that later. It has NXTP NATS messaging service. So the way that the SDK communicates with the rest of the Connext network and all the routers running is through NATS messaging. So this is a wrapper for handling the actual NATS messages itself. Subgraph is a wrapper around the subgraph. So we use the subgraph to determine what transactions are currently active, so that we don't have to like, or it's not really possible to read all the event data directly from the contract. What you need to do is look at events. So instead of looking through all the events on all the blocks ever since the contract was created, we use a subgraph for this, which keeps an up-to-date view of the data on the contract. We use this global state variable listener is established to keep the listener like listening to the contracts and stuff idempotent. So in the constructor, the constructor is how the class is created. So the SDK is basically imported into a JavaScript project or like a UI or React app or whatever, and then it's created using this constructor. So a user would pass in chain config, which at the minimum contains a mapping of chain IDs to a provider, which is a fallback provider. We're using a fallback provider so that we can have multiple providers attached to the actual provider instance. So this will give us like a little more durability in the provider itself. Then we provide ways to override transaction manager address and subgraph. If these are not provided, it will default to basically all the default stuff that is hosted, the subgraphs that are hosted, and the transaction manager that is basically deployed and is part of the contract package that is imported. Then we take a signer. So this signer will usually come from MetaMask, but it can also come, in the case of Node, it can be instantiated outside. We take an optional logger instance. We take the special variable that's do not start contract listeners. So this can control the contract listeners to reduce the number of RPC calls that happen. Because if you don't provide this, or if you say do not start contract listeners false, which is the default behavior, then all the contract listeners will start and everything will always be on and running contract listeners, which will use a lot more RPC calls. Then we provide ways to override NATs and auth URL and messaging. Arjun pointed out that we might want to make this a little different and have NATs URL and auth URL and have another way to basically point at testnet messaging and mainnet messaging. So we could have like an optional parameter that's like a network, and then it would be testnet or mainnet equals. I guess this doesn't have to be optional, it could be required, but let's do that because I think that is a good idea so that we can have different networks that we are running and we manage all the URLs for them. I'll write this as a to-do. So here we just instantiate the messaging class based on the messaging configuration that was passed in. So it uses NATS URL, auth URL. This can also default to undefined and it gets created properly within this class itself. Then we do some more configuration stuff here. So we create the configuration for the subclasses that we create based on the configuration that is passed in. So basically we'll get the deployed transaction manager contract address, which looks at the like NXTP contracts package, which gets exported from our artifacts that we deploy on chain. And then if the user overrides it, we use that. Otherwise, we get the deployed on chain. And then we create the transaction manager, and we do the same thing with the subgraph as well. Then we create the transaction manager subclass. We'll go into this later. But this is basically defined using the config that we're creating up here for each, for the contract and the subgraph. And then we either start the listeners now or we skip starting the listeners and do it later. Then we expose a function to connect the messaging. Since this requires like a signature from the user, we might want to not do this up front and do this later, or like give the user more control over this. So get active transactions is the first public function. So this will get all the transactions that are active. We can walk through this function first, and then we jump into the subgraph. So the subgraph class is a wrapper around the subgraph itself. So the subgraph is a structure for storing the data that is emitted from contracts. It gives an up-to-date view of the actual contract data using like an event stream based mechanism. So it's nice because in our case, it lets us pull active transactions and basically reconstruct like objects and entities based on events that have happened on the contract. Since we basically only store hashes and we don't store actual data, all the data is emitted through events and needs to be stored externally outside of the contracts in some kind of data structure like a subgraph. So what we do is we create this client, which is a typed client based on the schema. It's code generated from queries that we define in this queries function file. And then the first function is get active transactions. So this will take no parameters and it will return a promise, which resolves with like a bunch of the data from the transaction data, and it basically provides a status. So we determine a status of the transaction based on what the data gives us itself. So we get the user address. It has to be lowercase because all the subgraphs are lowercase, as we found out the hard way. And then in parallel, it will run a promise that maps all the SDKs, which are mappings of each chain. So each subgraph is per chain. So there's not like a subgraph across multiple chains. So we have to have multiple subgraphs for like a different subgraph for each individual chain. So what we want to do is we want to determine a status. So the status is that the active transactions can be in are either receiver prepared, which means the receiver already prepared the transaction and needs us to give our fulfilled signature so that somebody in the meta transaction network can fulfill it, or we have sender prepared transactions. So to determine what is a receiver prepared transaction, we simply get all the receiver transactions for receiver prepared on the subgraph for this user. So we pass in user and we get subgraph dot get receiver transactions. And then what we have to do is we have to find all the sender prepared transactions which don't have a receiver side. So this is to avoid overlaps, because you can have receiver prepared and there will also be a sender prepared, but you want just sender prepared. So then you want to filter out all the receiver prepared. So that's what we do with this. So we filter out everything on the sender prepared side that has a receiver prepared already. So now we have a distinct array of both receiver prepared and sender prepared transactions. And that's how we get that. So then we basically return all sender prepared and receiver prepared. We concatenate them. Receiver prepared has a status of receiver transaction prepared. Sender prepared has a status of sender transaction prepared. Then we flatten them out, and so we get one single array of all the transactions. Whew, that's the get active transactions. So get transfer quote. So this is kind of like the first step in the user generated process for getting a transaction or for starting a cross-chain transaction. So what it does, it takes in the parameters, validates the schema. If the schema is invalid, it will throw an error. Then it will destructure the params, check some more of the config. So if it doesn't have a configuration, setup. So if the SDK was not initialized with the proper sending chain ID and receiving chain ID, then it will throw another error. It will check the expiry to make sure it's greater than the minimum required, because since the router is gonna decrement the expiry on the receiver side, the expiry needs to be long enough to be able to allow for this to happen. Then we will set up some defaults. So if the user doesn't provide transaction ID, we create one. We default call to address 0 and call data. Then we encrypt the call data. So encrypting the call data involves, is the reason that we do this is so that the preparer does not keep the call data in plain text to avoid some kind of front running and things like that. This way, you only know the call data. The user only has to reveal the call data when they fulfill the transaction and not before. So we'll get the encryption key. So this is something that I'm not sure if this is going to work on Node.js or not. So we might need to think about that. That's also a note, Sanjay. We should think about how to do that in Node. If messaging is not connected, we connect messaging. So since messaging.connect pops up like a window, we don't want to do this unless we absolutely need to. So this is a time when we absolutely need to, because we're about to send a message on that. So now we'll connect it. So we generate a messaging inbox. So this is like a unique messaging. This is like a unique identifier for our messaging inbox. So we can listen to this and then we can subscribe to the messaging inbox itself. So what we do is we create a promise that will resolve when we get an auction response. So we subscribe to the auction responses at the inbox we create. Then we set a timeout to reject after 10 seconds, so that if we don't get a response within 10 seconds, we can basically like exit early an error and tell the user that there was no one available to fulfill their request. So each time we get a response in this subscription, we will check to see, of course, first if there was an error. Then we will check the router's signature on it. So the router needs to make sure that it signed the bid, or the user needs to make sure that it was actually a valid bid that was signed by the router, so it can like kind of hold it to that. This will come into play when we have our slashing staking mechanism. If the signer wasn't the router, it's going to error and then it's going to return. But if it was, then it will. So there's another to do here. So there's more checks that we probably need to do here. Check the contract for router liquidity. Actually, I'm not sure. Oh yeah, we should also probably check to do check response, because the router will send an estimate of the response. So we should check the response for received amount and make sure it's within a tolerance. Oh, and that's another good point. We should add slippage tolerance. Cool. So, and then this is going to resolve after the first one it gets. So another thing we need to do here is we need to wait for until we get like 5 or a few responses and then compare and pick the lowest response instead of just choosing the first one we get. So this is the promise that resolves when we actually get something here. So then after we set up this promise, then we can push out the auction request on this inbox that we created, and then we can await it here. So we're waiting up to 10 seconds for the response. If we get the response, we log that we received it, and then we return it to the user or the caller. So then the next step is starting the transfer. So when we have an auction response, we pass that into start transfer with the optional infinite approve. So this is the actual transfer mechanism itself. So what we do is we encode the auction bid so that we can pass this data on chain. It doesn't actually get checked on chain, but it is passed in to so that it can be fulfilled by the router, and the router can check and make sure that it actually did this before it fulfills it. So then what we do is we go into this transaction manager. So we interact directly with the transaction manager contract here, and we're using this never throw pattern that was explained in the router walkthrough a little bit. But basically it's like a functional pattern that has a wrapped result type that contains both potentially a result as well as an error response. So it allows you to handle a result um, while unwrapping it without dealing with the error until the very end. And it forces you to basically unwrap all the different results and handle the possibility of there being an error. So we'll call this approve tokens if needed. With this may or may not approve based on if it has been previously approved and if there is enough allowance. So if there was an approve TX, so if we did actually send an approval, then we need to wait for the result. And we need to send an event saying that we did an approve submitted. Otherwise, we can go ahead and just return from this. So once we get the approve receipt, if we get it, we have to check the status. And if there was a bad status on the approve for whatever reason, we're gonna error and hard error here. Otherwise, we will push out an event saying that we mine the approve and go on to the next step. So if all is good, then we're okay. And we say we completed the approval and we can move on to the next step, which is actually preparing the sender side TX. Prepare sender side TX. So I already validated the expiry. This is done up there. So we create the data based on the TX data here. Then we will call the prepare function. So this is also another result type. So we check the result at the end. If it's an okay result, we will send an event saying that we prepared it okay, and we'll return values. Otherwise, we will throw the error that came out with it. Okay, cool. So that's that function. Then the next step is finish transfer. So finish transfer is the next step of the process. So this happens after the router prepares on the receiver side. So once the router prepares on the receiver side, then we are allowed to broadcast our signature because we know it's safe. So we can broadcast our signature to the entire network as a whole and allow anybody to come in and fulfill it and collect a fee. So this method takes in params. It also takes in a fee and an optional use relayers method or param. So this either lets you use the relayer network or fulfill it yourself. So what we do is we sign the fulfill transaction payload. And if that works, then we get a signature generated. This is the bug you found yesterday, Sanche, so I fixed this. That was awesome. So then we wait for the messaging to get connected if it needs to be connected. Otherwise, we just return out. Then we submit the fulfilled to the receiver chain by, oh no, this is not this is the wrong comment. So now we have to basically decrypt the call data hash and make sure, and then because we need to get the right call data to be able to send. So if the call data is not just 0x and it's empty, then we actually need to get the call data out and return it back so that we can use it in the prepare transaction. So if we are going to use the relay network, then we will do it this way. So we will send a message through the messaging service to the meta transaction network, and we will wait for a response, subscribe to a response, and then publish the meta transaction request, otherwise error. So if that works okay, somebody will pick up our meta transaction and it will resolve. So otherwise, that means we want to send it ourselves. So what we do is we prepare it and call directly to the transaction manager, fulfill. This does require like a signer to be able to sign transactions on that second chain. So it would require basically the user to change the signer using a method that we've already exposed. So they would have to change the signer, and then they would have to prompt the user to change their MetaMask to the receiver side, which, is something that can be done, but we want to avoid having to do that all the time. So that's why we use this other thing, the meta transaction relayer. Then other method is cancel expired.
So the transaction manager we have right now, is this for receiving chain?
Yeah, so the transaction manager will go through that class, but you basically pass in the chain that you want to use.
Right.
So it's a wrapper around like a multi-chain transaction manager. So you just tell it which chain you want to fulfill on and give it the data, and then it handles all the stuff around finding out where the transaction manager is and what to do and everything.
Got
So then cancel expired. So we also expose a method to cancel expired transactions on the receiver side. So if the user gets a transaction prepared with it and it doesn't want to fulfill it for whatever reason, like say that the amount that the router prepared is like the wrong amount or something, or some other way that the router messed up, this will be a slashing condition eventually, but at first but then of course the user can get their funds back by canceling the expired transfer. So it's just a like basic interface into the contract cancel function. So change injected signer, like I said before, we have the ability to change the signer. This was requested by our integrator, Lee Finance, who said that they want the ability to control the chains on the front end and then change it dynamically within this. We also expose the listener method so that the users have more fine-grained control over the actual contract listeners and can attach and detach them. And then setup listeners. So this is interesting because it converts direct contract events on each chain to the actual sender transaction prepared and receiver transaction prepared. So what it does is it's going to attach on each chain. So the object keys chain config for each means for each of the chains, it's going to attach a listener, and then when it gets some data, it's going to check if the chain ID is a sending chain ID, it's a sender prepared transaction. Otherwise, it's a receiver prepared transaction. And similarly for the sender transaction, receiver transaction fulfilled and canceled. So this allows like the front end to know, rather than having to decide which chain and stuff like that, it can just figure out exactly that a sender transaction was prepared and resolved and fulfilled and whatnot. Cool. So other than that, the last thing I think is the transaction manager. So the transaction manager is basically a wrapper around all the different transaction manager contracts that are, sorry, one sec, that are basically configured for use. So this class is created by passing in a config again. So the config contains a provider and a transaction manager address. So that's all given in the like top level config. So that doesn't need to be really thought of here. So it will create a new contract. So this is like a direct ethers contract using the ABI and the provider for the specific chain that is passed in. And then it creates a listener. So this listener is, we can go into this actually. So this is kind of like a lower level listener for each contract. It will process the event data and pass it back. Basically, that's all it does, is just pass back event data from contracts into EVTs. So the EVTs basically give you a nice interface to do attach once and wait for, rather than just actually using these like raw listeners here. So basically we have a listener for each transaction manager contract on each chain in this chain config. So the chain config is a private variable here that contains for each chain a provider, a transaction manager contract. So this is an instance of the ethers contract and the listener, like I mentioned. So for prepare, in prepare, we basically just prepare a function. So we return this result async. So we call the prepare on the TX manager. And we do this connect here because when we connect, we want to connect using the injected signer. So if we have a this.signer, that means this was a signer that was passed in from MetaMask if it has a provider. Otherwise, we will connect the provider. So this is the case where like a Node.js can instantiate with a signer without a provider and then use the other providers that they passed in. So this gives you the ability to work with both a Node.js signer and the Ether signer, which has a provider already. Then it calls prepare and then returns like a error response if it wasn't okay. Then we basically do the same thing with cancel and fulfill. And then approve tokens if needed. So this will, this basically wraps the functionality around approving tokens for the transaction manager. So all you need to do is just pass in chain ID and asset ID of the token. And this takes care of like creating the ERC20 interface and checking the allowance. And if the allowance is there, then it will not create it. Otherwise, it will approve using the ERC20 interface, and you can pass it an infinite approve. So it will use the constant, so you never have to approve again. And then we have this getter, which is a get router liquidity. So the user can check the router liquidity itself. And this gives us liquidity in shares because that is what's stored on chain. Cool. So I think that's about it. Then the other thing is queries. So these are GraphQL queries that get translated into this typed SDK. So all we do is just query the transactions for a specific user, chain ID, blah, blah, status based on what we want to get. I think that's about it. I don't actually think we're even using this file anymore. I'm going to delete it. But okay, I think that about wraps it up. So that was the SDK.